The paper examines the impact of decoding methods on the alignment between large language models, LLMs, and human conversations. It investigates how beam search, top-K sampling, and nucleus sampling influence the quality of chatbot outputs, focusing on stylistic, psychometric, and semantic aspects. The authors present new measures of alignment, including politeness and negotiation characteristics, and apply these metrics to two datasets: Bolt SMS, chat, and Craigslist bargains. The results show that better alignment is attributed to fewer beams in beam search and lower values of P in nucleus sampling. Task-oriented and open-ended datasets perform differently, indicating the significance of context and interactions. This research aims to provide deeper insights into the practical applications of decoding methods and their potential to improve the human likeness of chatbot interactions, guiding future developments in chatbot design and deployment. Here is a combined summary of pages 3 and 4 of the research paper. The authors investigate the effects of decoding parameters on the alignment of large language models, LLMs, with human responses in conversation. They fine-tune a classifier on the empathy dataset and compute the cross-entropy score between human and LLM-generated utterances. Additionally, they measure verbosity as the absolute difference between human and LLM-generated utterance lengths and compute semantic similarity using BERT score. The authors experiment with various decoding parameters, including beam search, top-K sampling, and nucleus sampling. Beam search evaluates multiple hypotheses simultaneously, while top-K sampling filters out the K most probable next tokens and redistributes the probability mass. Nucleus sampling filters tokens whose cumulative probability exceeds a certain threshold. The results show that using two beams outperforms the base greedy decoding strategy, but increasing the number of beams diminishes this improvement. Lower values of P, 0.6-0.7, in nucleus sampling perform better, while P equals 1.0 demonstrates a significant decrease in alignment. Top-K sampling performs similarly to the base method across all values of K. The authors analyze turn-level results, finding that as conversations get longer, the LLM is able to more accurately emulate human traits. Notably, this trend applies for negotiation on the Bolt dataset but not on Craigslist bargains, where performance quickly plateaus. Beam search and nucleus sampling consistently outperform top-K sampling, indicating that alignment is correlated with the amount of context provided. To validate their insights, the authors compute correlation coefficients of the decoding parameters with the measures using multi-level linear models. The results show that top-K sampling does not have significant non-zero coefficients for any of the given metrics, while beam search has positive coefficients for negotiation and negative coefficients for verbosity. Politeness, negotiation, and verbosity all have positive coefficients for p-value and proportionally negative correlations for the number of turns. Overall, the authors conclude that the broader context of the datasets affects the quality of generated conversations, with task-oriented datasets like Craigslist bargains requiring more negotiation and resulting in higher semantic similarity across conversations. Here is a combined summary of pages 5 and 6 of the research paper. The authors investigate the effects of decoding methods on human-aligned conversational language models, LLMs. They find that lower p-values improve instruction adherence, while top-K sampling has a smaller impact compared to nucleus sampling. The best decoding method for human-aligned conversational LLM output is likely a combination of low-p nucleus sampling and beam search with a small number of beams. The authors also discuss the limitations of their work, including the usage of two specific aspects of style, politeness and negotiation. They acknowledge that their results are limited to these two aspects and hope to address this limitation in future work. The paper cites several references related to conversational LLMs, politeness, and negotiation, including works on modeling empathy and distress, hierarchical neural story generation, and psychological metrics for dialogue system evaluation. In the appendix, the authors provide details on the classifiers used for computing empathy and self-concept metrics. They trained fine-tuned variants of Microsoft's DeBerta v3 large model on annotated data to predict the presence of these attributes in the text. The authors also present the impact of instruction fine-tuning on the performance of LLMs. They show that fewer beams and lower p-values result in better human alignment for both LLM variants, with and without instruction fine-tuning. Notably, the model without instruction fine-tuning appears to show larger improvements in alignment when using decoding methods compared to the instruction fine-tuned variant. Finally, the authors justify the use of cross-entropy scores to compute stylistic and psychometric measures. They explain that lower cross-entropy scores indicate higher alignment with the ground truth human dialogue, making it a suitable metric for evaluating human-aligned conversational LLMs. This research paper presents a comprehensive analysis of the Llama 3 and Llama 3 Instruct models, focusing on their performance in generating responses that align with human-like traits such as politeness, empathy, and verbosity. The authors employ 6 psychological metrics to evaluate the model's output: politeness, negotiation, self-concept, empathy, verbosity, and semantic similarity. The study explores how different decoding parameters affect the model's performance. Specifically, the authors investigate the impact of the number of beams, p-value, and k-value on the generated responses. They present their findings in Table 2, which shows scores for each metric across various parameter settings. The results indicate that both models exhibit varying levels of human-like traits depending on the decoding parameters used. For instance, increasing the number of beams generally improves politeness and empathy scores but decreases verbosity. Similarly, adjusting the p-value and k-value can influence the model's performance on different metrics. The paper also highlights the importance of understanding the trade-offs between these parameters to achieve optimal results. By providing insights into the interplay between decoding parameters and model performance, this study contributes to the development of more sophisticated language generation models that can better mimic human communication patterns.